The topic of Module 10 is periodic motion. Now, periodic motion just simply means that you have a type of motion that is going to repeat itself over and over and over again. We've had one type of periodic motion that we've discussed already, and that's uniform circular motion. And so in uniform circular motion, you just have something that goes around and around and around and around in a circle, following the same path over and over again. And so examples of that would be the hands on a clock, which go around and around in the same path. You could talk about the path of a planet going around the sun. In uniform circular motion, it's a little bit elliptical, but we can certainly apply that as periodic motion because the motion does repeat itself over a period of time. But there are other types of periodic motion as well that we're also going to be discussing in this module. One of them is a pendulum. Where you just have something that's going to be swinging back and forth and back and forth. So whether it's a pendulum on a clock, like a grandfather type of clock, whether you have a child on a swing, both of those are repeating the same motion in the same path over and over and over again. Another type of motion that we're going to be spending quite a bit of time on in the first part of the module is what happens when you hang a mass on the bottom of a spring. And so if you have a spring that's suspended from a vertical position and you hang a spring on it, you hang a mass on the spring, that spring is going to bounce up and down and up and down and up and down. And so that's the type of motion. It's periodic motion because it repeats the same path over and over and again. And so we're going to be hitting that first. Now, in this specific type of periodic motion where you have a spring, Hooke's law is what is going to relate how strong the spring is, and the strength of the spring is related by a constant, which is represented by K, to the force that the spring applies. So what that means is that you have a spring, if you stretch it, the spring wants to spring back again. So the force that the spring applies to how far the spring stretches when you apply that force to it. And so the equation for that is, it's a very simple linear relationship. F equals negative K times delta X. And so in a few minutes here, I'll show you an example where we're going to learn how to use that. Before we get there, though, there's a couple of things about the motion of a mass on a spring that I want to make sure that you understand. If you just have this spring and you have it suspended, when it's just hanging there, that is classified as its equilibrium position. At this particular point in time, there is no motion of the spring, and the net force on it is 0. So that means that it's not moving. Remember that when we have a net force in one direction or another, that's going to cause motion. Now, if I would hang a mass on the bottom of this spring, then that mass is going to pull the spring down. And if you would pull the spring down here like this and then let it go, it's going to go bounce up and down like this, kind of boinging back and forth, because that's what springs do. They boing, right? Boing, 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 boing. So once you hang a spring on it, this equilibrium position is no longer the equilibrium position because it's going to pull the spring down further. And so it's going to be hanging probably maybe here instead. And so with the weight on it, this is going to be your new equilibrium position. And I'm abbreviating equilibrium with an EQM in case you're wondering what that says. So once you hang the spring on it, and again, once it stops bouncing, this is its new equilibrium position, because now there's no net force on the spring, because at this point the mass will have stopped moving. So the black line is where the equilibrium position of the spring is with no mass on it. Once I hang a mass on it, it now will have a new equilibrium position. Okay, now the restoring force, he mentions it in this section, but we'll get to it a lot more once we start thinking about the actual motion of this spring. The restoring force tries to pull the spring back to its equilibrium position again. So again, if I take the mass and I pull it down further and it starts bouncing, the force that the spring applies is trying to get it back to this position of equilibrium. So don't worry too much about the restoring force just yet. Right now we're just talking about the force that the spring itself applies. So with that in mind, let's look at example 10.1. I'm going to erase this at the moment so I've got room to work this problem. So if we look at example 10.1, it says this: a student hangs a spring on the ceiling with no weight on it. She then makes a mark on the wall to indicate the position of the spring's end, which is really what I did here. So this black mark is her initial position. After that, she hangs a 451 kilogram object on it, on the spring. She makes another mark to make the new position of the spring's end. If the mark is 2.51 centimeters lower than the first mark, what is the spring constant? So basically what we're saying here is that when she did this distance from where the spring was initially to where it is now that it has a weight hanging on it is 2.51 centimeters, and the mass of the weight was it 451? Yeah, 451 kilogram object. So obviously this is a very large mass that she has hung on the end of this. So new or old equilibrium position, new equilibrium position, and a difference of 2.51 centimeters. Now let's think about a force diagram of this object once it is down here. And I'm actually going to erase this one so that I don't confuse you. Okay, so the mass is now down this far, and our spring is now stretched further. Okay, so with the weight on it, it's now hanging right here. If we think about the forces that are acting on this mass, the mass is not moving. It is just sitting in one place. So I have the force of the spring that is acting up, and I have a force acting down, which is the weight of the object. Remember, weight is equal to mass times gravity. So what that tells me, since this mass is not moving, is that the weight of the object is going to be equal in magnitude to the force being exerted by the spring at this particular point in time. Again, keep in mind, this object is not moving, so these two forces are going to be equal in magnitude, but opposite in direction. And the equilibrium position, we define it as being the place where there is no net force acting on it. So to determine the total amount of the force that the spring is exerting on this mass, I only have to determine the weight of the mass, because I know that they're going to be equal in magnitude. So if I use weight equals mass times gravity, I have a mass of 451 kilograms, and gravity is going to be at negative 9.8 meters per second squared because it is acting downward. Remember that since we've got a vertical position here, we need to keep in mind which direction is positive and which direction is negative, and by convention we say that downward is going to be negative. So that gives us a weight of a negative 4,400 newtons, and it is acting downward. So what that tells me, again, because this is not in motion, that tells me that the force being applied by the spring is a positive 4,400 newtons. Okay? Now that I know what the force by the spring is, now I can use Hooke's law to determine the spring constant, because I know how far the spring has been displaced. So if force equals negative K times delta X, I'm going to have 4,400 newtons equals negative K times, now in newtons, a newton, remember, is a kilogram meter per second squared, so my delta X has to be in meters. So I'm going to change 2.51 centimeters to meters, which is going to be 0.0251 meters. And this also is going to be, I didn't allow enough space for it, this is going to be negative as well, because this is going to be in a downward position, okay? Then, as you can see, these two negatives are going to cancel one another out, and the spring constant is going to be positive. And so when I take 4,400 and divide it by 0.0251 meters, that's going to give me a spring constant of 18,000 newtons per meter. So what that tells me is that for every meter that the spring stretches, the spring is going to exert a force of 18,000 newtons. Okay, that is a very strong spring, and the spring constant, if it were smaller, would just indicate that the spring is not exerting as large of a force. Okay, so you're going to get some practice with using Hooke's law today, and then the next time we're going to talk about what happens when we actually put this spring into motion.